Hi everyone, we are in section 5.6, areas between curves, and we're going to look at a slightly different setup here in this problem. So here we are going to be finding the area between x equals y squared minus 4 and x equals 2y minus 1. So you might notice that that's different from our previous examples because those were all y equals a function of x type of functions. And here we have x, which is a function of y. So it's going to be a little bit different. All right, so let's start out by graphing our functions here. And this you might even need to refresh a little bit if it's been a while since you've graphed x as a function of y. But remember that this type of function here, x equals y squared minus 4, that's still a parabola. It's just on its side. So this is a horizontally oriented parabola that's been moved to the left by 4 units. So it's going to have a vertex here at -4. Okay, and then open outward from that point. So I'm going to put in our parabola here. Okay. Notice that this is kind of an interesting function because it doesn't like pass the vertical line test necessarily. That's because x is a function of y instead of y being a function of x, where we usually use the vertical line test. So kind of interesting. All right, so there are our basic points for the parabola. Top half there and bottom half here. And if you have trouble with the graphing, remember that you can always make a little table of points. It's just that you're going to be plugging in y values instead, so it does feel a little bit different. Okay, now for the next one, x equals 2y minus 1, that's still just going to be a line. And actually, we could figure out what that line looks like. We could solve this for y just to see a little better what that's going to look like there. 2y would equal x plus 1. So y is going to be 1/2 x plus 1/2. Okay, still maybe not the easiest thing in the world to graph, but it makes it a little bit nicer. There's our intercept there, and then we've got a slope of 1/2. Okay, so I'm just putting in some points now. And here is our line. Okay, so you can see the area that's trapped between these two functions. This is the area that we're going to be trying to find right here. All right, so we're going to need to set up integral for this. The intersection points, by the way, you notice that you can find those based off of the graph, or we could do the intersection trick again. I'll just show the intersection trick here real quick. Intersections. Okay, we would set y squared minus 4 equal to 2y minus 1. So we are going to be solving for the y values of these points instead of the x like we usually do. We have y squared minus 2y and then minus 3 equals 0. Factor that. And then we get our y values. Y equals 3 and y equals -1. So let's see the x values that those correspond to. Y equals 3, you could plug that into either function, remember, because this is an intersection point. That should be a point on both graphs. So I'm going to use the line. It's easier to plug in there. X equals 2 times 3 minus 1. And So you get x equals 5. And we can see that point 5, 3 right here on the graph. So makes sense. Agrees with the picture. That's good. Over here with y equals -1, x is going to be 2 times -1 minus 1. So that's where x is going to be -3. So -3, -1, yeah, that point is also on our graph right here. So that's also good. Okay, so there's our intersection points. Now we would need to set up our area integrals. Okay, and so far we've been setting up integrals in terms of x. So we're integrating things with respect to x using the dx, because that's what we had based our formula off of, was those little rectangles that looked something like this. My screen is glitching out a tiny bit. Let me see, there, if I zoom in a bit. And we had drawn in these tiny rectangles, and the width was delta x. That became our dx in the integral itself. So we're going to work with that. But let me stay zoomed in on the picture here, because you'll notice something a little funny when we try and find our top and bottom functions. Okay, most of the time, for most of this interval, the parabola looks like it's the top function, right? So there's our yt on top, okay? And then our bottom function would be the line, yb, right there. But notice how in our formula we are using y's, and these are not really y equals a function of x, so we're going to have to fix that. We'll have to solve these functions to be in terms of y, okay, or to make them y as a function of x so we can get those values. But also notice over here, okay, that at x equals -3, we have something different going on to the left of that. The top function here, yt, is still the parabola, but notice that here the bottom function is also the parabola, so that's a little strange. And why that can be the case here is because there are two halves to this parabola if we solve for y. All right, so y squared here is x plus 4, and when we take the square root of both sides of that equation, remember that taking a square root actually leads you to the plus or minus square root of x plus 4. And so that's what's going on here. Our top function in that tiny little region is the positive square root of x plus 4. And then our bottom function is actually just the negative square root of x plus 4. So that's what's going on there. It's the two different pieces of the parabola coming together. Okay. So yeah, we'll have to take that into account in setting up our integral here. Or shall we say integrals, because one integral is not going to cover this whole situation because there's a switch in our top and bottom functions. Okay, so here we would have to set up the area integral, first getting that little snippet with the two pieces of the parabola. We'd have to go from -4 to -3. Notice that I am using the x values to do this. X equals -3 there. So -4 to -3, taking that top half of the parabola and then subtracting the bottom half of the parabola. So square root of x plus 4 minus the negative square root of x plus 4, dx. And then we would have to add the rest of our area that goes from -3 all the way to +5 over there. -3 to 5. And in that case, the top function, yt, that's still just the positive half of the parabola. And then our bottom function is the line. And thankfully over here, we already converted that to y as a function of x. So we can use that to our advantage here. Okay, so for the second integral, we would have square root of x plus 4 minus 1/2 x plus 1/2 dx. Okay, now let you guys do that if you feel like it. And this is doable, by the way. You could actually do this problem this way, but let me stop you before you go off trying that. There is an easier way to do this. So if you want to try this one this way as practice, you can sure do that. But let's look at a more efficient setup here. Okay, so that, meh. Our idea for this is going to be to change our direction of integration. We are going to use horizontal rectangles to set up our Riemann sum and thus our integral, instead of doing the usual vertical rectangles. Okay, so instead of integrating with respect to x, we're going to integrate with respect to y instead. All right, so when we do this, let me draw a kind of reduced form of our graph here. Okay, 1, 2, 3, -4. All right, 1, 2, 1, 2, 1, 2, 3, 4, 5, 5, 3. Sorry, this part is not super exciting to watch, I know. But good practice, I guess, graphing horizontal things very quickly. Okay, so there's our parabola basically, and then our line goes through 1/2, basically like that. Okay. Pretend those are intersecting at 5, 3 right there. Okay, so yeah, here, using horizontal rectangles instead means that in order to set up our Riemann sum, we are gonna sketch our little rectangle, which is gonna be very, very thin, by the way, because we're gonna ultimately take an infinite number of these little rectangles. There's one little sample guy. All right, so one little rectangle here, we want to see what the area of that looks like. That way we can add up an infinite number of areas and take our integral. Okay, so one little rectangle will look something like this. And notice that instead of having a tiny change in the x direction, delta x or dx in the integral, we have a tiny little change in the y direction. So we're going to use delta y here and dy in our integral. Okay. And now for the width of this rectangle, because delta y is the height. All right, for the width of this, we would want to take the difference between this x value on that end and this x value over here on this end. We would want to find the difference between those. So we would take the larger minus the smaller. So we're going to say that as doing the right function minus the left function. Okay, so the x on the right minus the x on the left. Okay, and then just to clarify, if you wanted a different, set a different way, this is the larger x value, and this is the smaller x value. Okay, so the area of one tiny little rectangle, we would multiply the width times height. Okay, and so I'm just going to abbreviate that as XR minus XL for the width and delta Y for the height. And so when we take our Riemann sum, when we get the full total area here, we're going to take the limit as n goes to infinity and add up an infinite number of these little rectangle areas. And we know that that is going to turn into the integral. So our integral is going to look like this. It's a definite integral still. We'll say it's from C to D, so it looks a little different from our previous limits. And then inside, you're going to have XR minus XL. And then that delta Y right there is going to turn into dy for the integral. Okay. So yeah, this is the other way that you can find the area of a region here. And when you're doing this integral, notice that it is dy with respect to y. So your functions need to be written in terms of y. Your limits need to be y values. So I'll just make a little note here that everything in this whole integral is in terms of y. Let any x's sneak in there. Okay, the XR and XL are just placeholders. You're going to put in those functions in terms of y. All right, so let's do that for this situation here. Okay, so now our area integral is going to be from our lower y value limit to our upper y value limit. And so checking those intersection points again, notice that we had our y values for the intersections right here. So we're going to integrate from -1 to +3. Okay. So integrate from -1 to +3, and then our right function, xr, is right here. xr is the line, and our equation for that line was right here. X equals 2y minus 1. So there you don't even have to solve for y or anything. X is a function of y, so we want to keep it that way. All right, so xr is 2y minus 1. And then our function that's on the left with the smaller x values, xl, is the parabola, and that's y squared minus 4. Okay, so when we set up our integral here, we're going to take 2y minus 1, xr, minus y squared minus 4, and integrate with respect to y. So what that means is that we're going to be adding up all these little rectangle areas. We're going to be stacking them up from y equals -1 all the way up to y equals +3. And so that would start down here with a little rectangle, and then you'd stack another little rectangle on top. So you'd be stacking up these little area rectangles in the y direction. There's our sample rectangle, and you'd stack them up until you got to y equals 3. And so that's showing that same area, just in a different way. But in this case, the integral is a lot nicer. It's only one integral. There's no square roots in here. And yeah, it's all pretty nice. We can simplify this integral from -1 to 3. And that turns out to be just 2y minus y squared and then +3 dy. And that you can find the antiderivative of fairly easily and plug in your values. Let you guys check that, but the area that you get should be 32 thirds. So a little bit of math magic there at the end for you guys to fill in, but that is the area that we get. If you want to try it with these two integrals up above, you can do that as well. You should end up with the same answer because it is describing the same area. But personally, I think this integral looks a lot more approachable. So yeah, you can do things with respect to y instead.